Okay, we're back at it again, talking about wave optics, and in this video we'll talk about um, diffraction and the effects of different wavelength and get into color. So let's remember some things that we got into last time, and that was that light going through a double slit setup will produce an interference pattern on some screen which is behind it at some far distance away, and there will be a central maximum followed by minima on both sides, followed by more maxima, followed by minima, etc. And we did an example. And then in the assignment, I put a link to 3 different videos. They're relatively short. At least the second one about the double slit with the red laser, you should only watch a minute or so of that to see what's going on. But it turns out what happens is if you send light through a double slit, for example, if you send light of one color, monochromatic light of, let's say, green, you'll end up with a pattern that looks like the top figure. But if you send white light through the same double slit setup, you'll end up with this pattern in which there is sort of a rainbow shape going on. So can we explain what is happening here? Let's see. Can we? Yeah, we can. Good. We can explain it because we have an equation that describes this whole setup, and I'll let you go back to remember the origins of that. Well, at least I'll quickly sketch out what's going on, right? You've got your thing, your block, your object, in which there's 2 slits cut. They're spaced out by a distance d. Very far away, you've got your screen. And actually, let me draw it like this. And what I want to do now is kind of plot what the intensity is doing as a function of distance. So if I plot intensity or brightness, maybe I'll just do that, brightness, then what you'll have is it'll be very bright at the center, and then followed by 2 brightness minima, followed by a maximum which is not quite as big as the central one, but then another minimum, and the same thing over here. And the location of these peaks, for example, is determined by a formula which relates, more or less, this angle, theta, to d and the wavelength of light. And that formula was something like d times sine of theta was equal to m lambda. And if you think about it, you can solve this for theta, or you can solve this for the position along this y-axis. So there was another equation we wrote down, or we derived the location of the mth bright spot was equal to m lambda L over d. The point is the position of a bright spot depends on the particular wavelength of light. So what that means is that if you think about how these things go, basically longer wavelengths, longer lambda, will give you, if you just focus on this formula, longer wavelengths will give you bigger sine of theta, which means bigger theta. And I'm in a new location now. What that means, longer wavelength, bigger theta, what that means is that, well, the pattern that you see here will be different for longer or, shorter wavelength. So for example, if longer wavelength gives you bigger theta, shorter wavelength gives you smaller theta. So if you're looking at, say, red light, you know that blue light has a shorter wavelength. So the pattern that you might expect to see for blue, it would still be peaked, at the center. I'm not sure exactly how to draw this, but maybe okay, I'll just put it slightly different. So it'll still be peaked at the center, but the location of the first minimum and also the first order maxima will be kind of more like this, just for example. So everything kind of gets crunched or scrunched to a different location. And so what you end up getting is, if you send perfectly white light through these slits with all the colors inside, they come out and they create this interference pattern, which is visibly separated because each color corresponds to a different wavelength. Um, yeah, okay, so there you go. That will hopefully explain that phenomenon. Um, the last thing to get into is you may wonder, how do prisms work and how do rainbows work? So, in order to understand that, what we have to understand is the relationship between refraction and wavelength. So when we first talked about refraction, this was in the context of geometric optics, where we didn't even refer to light as a wave. We just treated it as these rays that go in straight lines. But what it turns out is the speed of a wave, so I'll just call it v, the speed of a light wave inside of a material, I guess, and really you could say this is the speed of any wave. On some level, this is true. Is some function of the wavelength of the light, or the wavelength of the wave. Now, in totally free space, in vacuum, the wavelength of light does not affect its speed. But once you're in a material, then this changes. And typically, what goes on is that this is I'll say it like this: monotonically increasing function of lambda. Monotonically increasing. And so, it's hard for me to say exactly what this would do, but if you plotted speed v as a function of wavelength, eventually there will be some point where the wave speed is equal to c. And I don't precisely know how exactly this function will go, and it might even depend on the medium, but that whatever the function looks like, it's got to do something that sort of continually increases and kind of approaches as some kind of asymptote. What that means is that the index of refraction, n, which of course, remember, is defined as the speed of light divided by the wave speed. Well, that means the index of refraction is also a function of lambda, right? It depends on c divided by v as a function of lambda. Since v continually goes up with lambda and it shows up in the denominator, the consequences are that n is monotonically decreasing. Monotonically decreasing with lambda. And, well, the consequence of that is that if you were to take a prism and you were to send in light one moment. Oh yeah. If you were to send in light of a particular wavelength, like let's say, let's send in red, I guess. You send in red light, and just fair warning, this isn't going to be a great picture, but some amount of light goes into, and let's say the prism is made of glass or water or whatever, then it will bend, and it will bend going, right? It breaks at a smaller angle, and then when it gets out into the other medium, it breaks at a bigger angle again. So the path, you got to be kidding me with this. It would be something like this. But I'll let you check this, the way that the math works out, that the wavelengths that are smaller feel a slightly bigger index of refraction in the medium. So as they travel on paths along the same path, they will break slightly more and then break slightly more. And so there will be a separation of color based on wavelength. And for this, you may recall the cover of Pink Floyd's Dark Side of the Moon, but basically that is why a prism does what it does, and why you're able to see, rainbows coming through various pieces of glass. And the last thing to do is just simply to show you how rainbows actually work. And so now that you have all the tools that you need to know about reflection, refraction, and the wave nature of light. So in this picture, it's just describing how white light comes in, could be from the sun or anywhere else. That light, once it hits a water droplet, is refracted, meaning that it's bent slightly, and it's bent in a way that depends on the wavelength. Some of that light, of course, does get reflected at the surface, but a lot of it gets refracted through. So that's what you're seeing there. So some is reflected off, but a lot goes through. It gets to the next medium. A lot can make it through, but some is reflected. And so that internal reflected part goes along. And then finally, when it leaves the water droplet, it's refracted again, going from the water to air. And so there are two instances where refraction happens, namely here and here. And it's the combination of those two things which give you the spreading of the light into the constituent colors.